Hi, welcome to the third Applied Maths for Games Development video. This one's about forms, bases, and notation. So we'll start with standard form and expanded form, which is one of the simplest things we learn about maths back in school. Standard form of a number is to write each digit in its place, with the digit at the right being the one that's smallest in value, also called least significant. So for example, 500 is written as 500, so the 5's the hundreds. Sometimes you put a comma after every three digits, so you get thousands, millions, etc. More on that later. But some other parts of the world use a dot instead of a comma to indicate these place values. If you see in code, for example, the culture of a number being described, that means whether we use dots after every three digits or commas or perhaps something else. Expanded form is where you write each digit separately. So for example, the number 1275, you write that as 1 times 1,000 plus 2 times 100 plus 7 times 10 plus 5 times 1, which may seem a bit counterproductive, but it is useful later on when you start to compare how we do things in decimal to in other bases, which is why I'm telling you about it just now. So moving on, we've also got decimal form, fractional form, and mixed form. So if something's written in decimal form, it has a decimal mark and no fraction part. So for example, 2.5, 0.001, or 4,275.0. In fraction form, it shows a number as just a fraction. So for example, a half or 11 hundredths or 512 over 2, which can also be written as mixed form. Mixed form means you've got an integer part and a fractional part. It's not just a fraction. So this is written as things like 5.5 or 15 and 17 hundredths or something like that. Moving on then, next up we're looking at bases, and a number base determines how many digits there are in your numbering system. So we mostly use decimal. This is base 10, so it has 10 symbols from 0 to 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And by combining those symbols, you can make any number you like in decimal. There are infinitely more bases, but only a few of them which are actually used, and certainly only really two of them which are commonly used in computing nowadays. So there's binary, this is base 2. Because it's base 2, we only have two symbols, the 0 and the 1. There is octal, which is base 8, which used to be used, but it's now pretty rare. So with 8 symbols, you've got from 0 up to 7. 0, 1, 2, 3, 4, 5, 6, 7 is 8 symbols. Really only included, so you can compare it to the next one, hexadecimal, which is base 16. So with 16 symbols, we will run out because you've only got 10 symbols for numbers, 0 up to 9. And when you get past that, you have to use letters. A, B, C, D, E, and F represents 10, 11, 12, 13, 14, and 15 respectively. So every time you see an A, that's meant to be a 10 in that column of digits, for example. All right, let's compare the bases then. So base 10, also called decimal, you know this from primary school, but it's worth repeating so you see the similarities to how we do things in other bases. So each digit has a value. Along the top there you can see the thousands column, the hundreds, the tens, the ones, the tenths, the hundredths, and the thousandths. But you can also write that value as an exponent. 1,000 is 10 to the power 3. 100 is 10 to the power 2. 10 is 10 to the power 1. And if you carry that on, you'll see that 10 to the power 0 is the units column. That 10 to the power 0 is only equal to 1. In fact, pretty much any number, except possibly 0, any number raised to the power 0 gives you 1 as the answer. So that column will always be the units column. That will always have a value of 1. If you continue going, you get 10 to the power minus 1. And that's the inverse of 10 to the power 1, which means it's 1 over 10 to the power 1, or 1/10. The next column, the hundredths, that's 10 to the power minus 2. So that's the same as 1 over 10 to the 2, 1 over 100. So it's a hundredths. And next to 10 to the power minus 3, so that's thousandths, and so on. So you've got an example there, 5135.125. That's why I showed you expanded form there earlier. That's 5 thousandths, 100, 3 tens, 5 units, 1/10, 2 hundredths, and 5 thousandths. You could write that in that long form if you really wanted to. You probably wouldn't want to in base 10, but you might want to do that in other bases. Let's have a look. Here's base 2. So base 2 is in binary, only zeros and ones. Very useful because it can represent a whole bunch of clearly defined physical states. For example, You could measure memory voltage. Let's say you've got voltage from 0 to 5 volts in your memory cells. You could say that has the values from 0 to 5. But would you be certain that you could measure completely accurately the difference between 3 volts and 4 volts every time without fault? It's much harder to do than just saying, let's have a 0 for on, and a 0 for off and a 1 for on. So that's why binary is useful to store in memory as voltage. It's also useful in hard disks, which are magnetized either north or south. There's no third option, only a 0 or a 1. And on a CD or DVD or Blu-ray, the laser is either reflected into the receptor or not. So you've got only two options, binary again. Lots of physical things are binary, so it's useful for representing numbers. Binary is also useful for things called bit masks, which we'll see later on, and bit shifts, which helps with algebra being more efficient in the processor. But look at that table at the bottom. You've still got the units column, which is 2 to the power 0. But if you go in either direction, the exponent goes up or down. So you no longer have a tens and hundreds columns. Instead, you've got 2 to the power 1, 2 to the power 2, 2 to the power 3, etc. So you've got 2, 4, the 8s is missing there, 2, 4, 8, 16, 32, 64. So each column has a value twice that of the last column. And if you go to the right of the decimal place, the same thing happens. You've got halves, quarters, 1/8, etc. And that's more or less how numbers are actually represented as floating points. So the example at the bottom there, remember the 8s column is missing, I do apologise, but you've got 1 lot of 16, 1 lot of 4, 0 lots of 2, 0 lots of 1, 0 lots of a half, 1 lots of a quarter, and 1 lots of 1/8. Add them all together and you get 20.375. So that's that number in binary converted into decimal. What about base 16? Well, that number we just saw, it's kind of hard to read, and converting it to decimal isn't a trivial process. So hex is more of a compromise. Computers don't actually work in hex, and neither do humans, but hex is more readable than binary. Not quite as good as decimal, but because we need to use A to F as letters, as digits. But also, it's much easier to convert from hex into binary and vice versa. So it's a compromise, but a useful one sometimes. Quite commonly used in things like defining colors, network addresses, editing your save games. That's where you'll probably see hexadecimal used. And look at the bottom. You've got, again, columns. You've got the units column, which is 16 to the power 0. You've got the 16s column, which is 16 to the power 1. You've got the 256s column, which is 16 to the power 2, 4096s, and so on. And again, to the right of the decimal place, you've got 16ths, 256ths. You would have 4096ths, and so on if you went further in that direction. And the example, you've got 1 lot of 4096, 3 lots of 256, and that A, that's a 10 number, so you have 10 lots of 16. No units, no 16ths, and 5 25ths. So add them all together, you get 4864.2. So that's hex into decimal. Converting hex into binary is relatively simple. You've just, every 4 digits of binary is the same as 1 digit of hex. And included for completeness, but not used much anymore, is octal. It's got 8 to the power 0 and then 8 to the power 1, etc. So you've got 8s, 64s, 512s, etc. And to the right of the decimal place, you've got 8ths, 64ths, 512ths, etc. And conversion is much the same. 2 lots of 512, 4 lots of 64, 2 lots of 1, 2 lots of 1/8 in that example. Add them all together, 1283.25. So that's bases in a nutshell. There's a lot more to them, but let's move on for now to notations. Now, maths has loads of notations: algebraic notation, radical notation, vector notation, calculus notation, and plenty more. And we've already seen a bunch of this, but there are some that are often referred to by name specifically. One of them is scientific notation. So in scientific notation, numbers are split into a mantissa, a base, and an exponent, and usually it's base 10. So in scientific notation at least. So we don't often mention that, except when we see it there. So scientific notation puts these three together: mantissa times base to the power of exponent. For example, 5 times 10 to the 6. That is the same as saying 5 times 1 million, because 10 to the power 6 is a million, Effectively, when you see that number, 10 to the 6, tells you how many zeros you've got in that set at the right-hand side of that multiplication. So 10 to the 6, you've got a 1 with 6 zeros, or a million. So 5 times a million, 5 million. 5 times 10 to the 6 is 5 million. Useful for very large or very small numbers. So the mass of the star Betelgeuse, that's its real name, 15310000000000000. I can't even read all that. That's how many grams it is. It's a mouthful, and it's also hard to write without making mistakes in how many zeros. But if you say 15 times 10 to the power 33, we've counted the number of zeros, there's 33 of them. That's a lot harder to get wrong because there's a lot less numbers. So in scientific notation, if you want to multiply together two numbers that are in scientific notation, it's m times 10 to the a multiplied by n times 10 to the b gives us mn times 10 to the power a to b, a plus b, sorry. You know what, I might just load up Paint and show you an example there. So let's say it's 3 times 10 squared. I'll put that in brackets just for clarity. Multiply that by another number in scientific notation. Let's say 2 times 10 to the power 3. Now we could work that out by hand. So 3 times 10 to this 2. 10 squared is 100. So 3 times 100 times 2 times 10 cubed. 10 cubed is 1,000, so that's 2,000. What's 300 times 2,000? Well, it's 6 and 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5. And we can put a comma in there, we get 600,000. That's fine and dandy when you've got relatively small exponents. Imagine if that was 10 to the power 20 and 10 to the power 30. You'd be there all day. So let's try the shortcut route there. In this case, m is 3, n is 2, so 3 times 2, times 10 to the power a plus b. So times 10 to the power of a, which is 2, plus b, which is 3. So 3 times 2, 6, times 10 to the power 2 plus 3, which is 5. So 6 with 5 zeros. 1, 2, 3, 4, 5. It's given us the same answer. Good. Oh, that would have been embarrassing. Okay, so that works. That's how you multiply two numbers together in scientific notation, which is useful if you've got big exponents. To divide two numbers is much the same, but if you've got m times 10 to the a divided by n times 10 to the b, instead of multiplying m and n, you divide them, and instead of adding a and b, you subtract them. Sorry, before I go on, adding and subtracting numbers in scientific notation doesn't have any quick shortcut. You'll have to either work them out fully or standardize them so they're both to the same exponent. I would go with the second route, to be honest. So scientific notation numbers can be normalized. Unfortunately, normalize as a word, or normal, is used far too much in maths for different things, and it can be confusing. So if you look this up, be aware that normalize can mean a bunch of different things, and it does depend on the context. But in the context of scientific notation, normalizing a number goes like this. Shift the decimal place to the left or the right until there's exactly one digit, which is not 0, on the left of the decimal place. So for example, 1.3 or 9.7, not 0.4, because it's got to be a non-zero digit. As you do this, don't forget to increase or decrease the exponent, otherwise you're actually changing the number. But if you multiply by 10 and then decrease the exponent, then effectively you're multiplying and dividing by 10, so it cancels out and you've got the same number, so you're allowed to do that. For example, 1531 times 10 to the 31. That is the same as 1.531, the decimal place, which wasn't visible before, has moved 3 steps to the left. So the exponent has increased 3 steps to compensate, but those are the same number. The one on the right is normalized. The one on the left, there's nothing wrong with it, it's just not normalized. Next, we've got engineering notation. So scientific notation has its upsides, but the numbers can still get confusing. So engineering notation uses prefixes, and everything has an exponent that's just a multiple of 3. You don't get 10 to the power 2 in engineering notation. I'll start with the exponents on the right there. If you've got an exponent of 3, 10 to the power 3, that's thousands, and we use the System International prefix, kilo, so kilometers or kilowatts or kilograms. And then if it's 10 to the power 6, that's millions, and that's mega, like megatons of explosives or something like that. 9 is billions, which is gigawatts, whatever you like. 12 is trillions, which has got the prefix of tera, and so on. On the left-hand side, you've got negative exponents. So 10 to the power minus 3, that's the same as 1 over 10 to the 3, or 1 over 1,000. So that's your thousandths. And that's represented by milli, so milliliters, milligrams, that sort of thing. Then you've got microliters, or whatever you like, minus 6. Nano something is minus 9. That's billionths, and so on. Oh, by the way, billions. It says they're American short scale term. And that's because technically a British billion is different. It's 10 to the power 12. I'm not too keen on that naming system, to be honest, and it is, I think, kind of dying out. But having billions as 10 to the power 9, that is the American version. Next up, we've got orders of magnitude. An order of magnitude is basically the exponent of a number if it was written in scientific, well, a certain type of scientific notation. So for example, the order of magnitude of a number like 4 times 10 to the 15, we would often say that its magnitude is 15. It does depend on how you define magnitude, unfortunately, but we'll get back to that. The number 6,798, the order of magnitude of that is 3, by the standard I'm using here at least. However, this is one of those things in maths where different people have a different take on it. Some people say 399 should be 3.99 times 10 to the power 2, or magnitude 2 in other words. Some people say 399 should be 0.399 times 10 to the 3, which is order of magnitude of 3. Some people even say they should use the square root of 10 as a dividing point, which is a kind of a logarithmic approach. I'm not keen on that at all, to be honest. But the point is, there are different ways of approaching it, and none of them are wrong. They're just different notations, I guess you could say. So as long as you're consistent about it, you can pick any one of those approaches and get the right answer. So when you're programming in decimal notation, in C# and other .NET languages, most types that you have available to you have a .toString method, which you can use to convert it into a string for outputting to screen, for example. You can also pass in a parameter though to specify which format and culture to use. So for example, here is a number being told to convert to a string using a fixed point format, hence the letter F, and 3 decimal places. So it's going to say F3. So write out the number with F being equal to 12,345. So if you write that on the screen with the format of a fixed point decimal, 3 decimal places, the output you get on the right there is 12345.000. So if you want numbers to line up, for instance, if you've got currency and everything has 2 decimal places, that's useful. ToString method can also use decimal format with commas. This is the N type. I think it just stands for number, not engineering, although it is useful for engineering format. Again, tell it a number of decimal places as well. So for example, N2. If you give it a long number like that, it's kind of hard to tell exactly what that number represents, but convert it to N2 format, and you'll quite easily see the commas appear on the right hand side there, and that will help you see that it is 12,245,000,000. Then you've got scientific notation. ToString can also do this by putting in E as the type. E is short for exponential. It's another, well, it's not exactly the same, I guess, but it's basically scientific notation. And again, tell it a number of decimal places. So for example, that same number, if you tell it to write it as an E1 type, that's exponential with 1 decimal place. So that 1 decimal place is rounded off. So 12345000000. It should really say 1.2345 with an exponent of 10. But because we've told it to only use 1 decimal place, it rounds it off to 1.2 exponent plus 10. That's basically saying 1.2 times 10 to the power 10. Okay, so moving on to some other notations. We've got sigma notation, and unfortunately this does have a scary math symbol in Greek. It's sigma, of course. It's a capital sigma. I'm sure you all know your Greek alphabet and can easily tell that's a capital sigma. So it looks like that. Scary, right? So you've got the number n being used in the sigma notation, and n goes from 1 to 5. That's what those numbers above and below the sigma mean. So that Greek symbol is your boy sigma. Sigma just means sum though. Nothing special about it. It just means add stuff up. What are we adding? We're adding n. And what's n? Well, it's every number from 1 to 5. So this means sum up all the values of n, excuse me, all the values of n from n equals 1 up until n equals 5. And in sigma notation, it's always integers that are used there. So if you add up 1 plus 2 plus 3 plus 4 plus 5, that's another way of saying that sigma notation that you see up there. Hopefully that's helped demystify it slightly for you. If you do it in code though, basically sigma means a loop where you're adding something. So that same sigma notation converts into this code. Start with a result of 0, and then loop through from n equals 1 till n equals 5, and your result adds on n each time. So result will be adding on 1, then adding on 2, then adding on 3, then adding on 4, then adding on 5. Might seem like it's not helping much there, but imagine if it was n equals 1 to 1 million. This leads us to recurrence relations. It's not technically a notation, but it is a similar idea to sigma. So for example, an equals 2a n minus 1. That's an example of a recurrence relation. So if you have a number a n minus 1, then you can work out the next number a n by simply doubling it. So to work out a when n equals 4, if n is 4, you need to know what a was when n is 3. And to work out what a is when n is 3, you need to know what a was when n was 2. And you need to know what a was when n was 1. And that's usually where you start. So here's, for example, a n equals 2a n minus 1. That subscript tells you which number in the recurring sequence we're looking at each time. But if we start with the first one, if a equals 1 at the start, then we can go from, well, the x on the right hand side there, that's the first value, and it keeps on going until we reach, for example, I've just picked this number out thin air, but if we do this recurrence relation 5 times, then we'll go from 1 to 5, and each time a is going to be doubled, because we said 2a is the actual relation between them. That's recurrence relations in a nutshell. They can get pretty complicated though, but it's just a for loop. And now we've got big pi notation. Now I quite like a big pi, but this is another big scary Greek letter, capital pi. A little bit different from lowercase pi, which is the number 3.14159, etc. Big pi is used to represent something similar to big sigma, but instead of repeatedly adding stuff, we're repeatedly multiplying stuff. So for example, the factorial function can be defined like this. N factorial is equal to big pi of k from k equals 1 up to n. Bit of a mouthful, but it just means keep on multiplying by k from 1 to n. So you multiply from 1, k equals 1 at the bottom there, up, multiply it by every number from then upwards until you reach n, and that's your factorial. And that will do for now.